All right, so, oh, this is not lecture one, but today we'll talk principal components analysis, okay? And so, have you guys encountered PCA in any other classes right now? Or other classes in general? Yeah, okay, like one of you? Okay, so most of you have not, and that's totally fine. So the big idea in PCA is that you start off with a data set with many variables, okay? And the variables in this data set are possibly correlated, okay? Most likely they are, all right? So, I mean, for them not to be correlated means you have like two completely independent variables. But in general, there's some kind of relationship between the variables, which means there's a little bit of, to some degree, some redundancy there, okay? And so, so the variables in the data set are correlated, and what PCA does is it's going to transform the data into uncorrelated variables, okay? So we start off with correlated variables, and it transforms the data into uncorrelated variables. And the goal is often to go to perform dimension reduction, okay? So if we take advantage of the fact that the variables start off correlated, can we reduce the number of variables and still capture or convey kind of the variation that exists in the data, okay? So when we transform the data into uncorrelated variables, usually we can just try to keep maybe a few of these uncorrelated variables that capture a lot of the variation, okay? So let me I'll just start off with this example, okay? So maybe you've got a data set on housing prices, okay? And this is often, a data set that gets used for any kind of like large either regression or data mining or some kind of class project. You might deal with some housing prices. This is a common thing. And a lot of these data sets, there's going to be a ton of variables, okay? You're going to have things like the livable square footage, the total square footage, or they might break it out into like basement square footage and I don't know, some kind of like loft thing or something. You've got like number of bedrooms, number of bathrooms, lot size, if there's a pool, roof style, what kind of central, AC, is it central heating or not, or things like that, garage, carport, parking space, the date it was built, the quality of the kitchen, the quality of the floors, the roof quality. I guess I've listed so many. There's other things like the location and the zip code, the local school rating, the local crime rate, the local income level, stuff kind of about the neighborhoods and things like that. And so there's all of these variables, and if you, I don't know if any of your families have gone house shopping with you, there's all sorts of things to consider, okay? You might have had like a small taste of this when you had to like find an apartment, but generally when you're looking for an apartment, you're just stuck with whatever's close to campus, and so that limits your options severely. But after you graduate and you're working, you might be looking for an apartment or you might be looking for a house, and you have all sorts of things to consider, right? Like which neighborhood. You probably want to talk to your colleagues at work and talk about which neighborhoods are nice areas to live in and things like that, and those are all sorts of things to consider. And so you're going to have a bunch of these variables. I argue that we can reduce all of these variables into basically three key aspects of a home that you might consider purchasing, okay? One is going to be basically measures of size. So things like the square footage, the number of bedrooms, the number of bathrooms. Those are all related to the size, okay? You're not going to have a huge house with only 2 bedrooms. You're not going to have a tiny house with 5 bedrooms, okay? It just doesn't kind of work that way. So they all kind of go together, and again, number of bathrooms and number of bedrooms they increase or decrease together. So you're going to have something about size of the house. And I would say another variable will be kind of the amenities and quality of the house. So does it have, in general, if the house has redone its kitchen, its floor has probably also been redone in the past, 5 or 10 years as well. You generally don't have one part of the house falling apart, like the roof is falling apart, but the kitchen has, they just spent $20,000 redoing the kitchen or something like that. So these things generally correlate together as well. And so, and other amenities like, those are all kinds of the things that go together. And then the other component that's also very important is basically neighborhood desirability, okay? And so things like the local school rating going up will be higher, a more desirable neighborhood, low crime rate, sad to say, but, higher income levels and all of these things all are tied to kind of neighborhood desirability. And so they don't necessarily have to all have positive correlations, but these variables will generally be strongly correlated together. And so rather than having to look at a list of like 15 variables, you can just kind of give a house like a score on these 3 and just say like big size, high quality, high neighborhood desirability, and this will be like a very expensive house, right? And then you have to kind of decide like what trade-offs you would want to expect. If you had to pick 2 out of the 3, which are the 2 that are most important to you, and things like that, right? And so these are. So this is kind of the idea of like data dimension reduction. Okay. There's a ton of other aspects or examples of dimension reduction that you guys are probably familiar with, okay? So the GPA, your GPA is an example of dimension reduction, okay? Every one of you has like taken a bunch of classes and stuff, different classes, you've done well in some, done poorly in others, or things like that. And they all just get averaged together down into a single number. And that one number is somehow supposed to capture your academic performance, okay? And of course, I always emphasize that your academic performance does not reflect who you are as a person, and that's absolutely true. And furthermore, this GPA, this single number, is, because it's dimension reduction, loses a lot of information, okay? So there might have been a quarter where there were like personal issues going on with your family and things like that, and because you value people and relationships more than your grades, which I strongly emphasize, you decided to sacrifice your schooling so that you could help with your family, and that might have reduced your GPA, okay? But that dip in the GPA doesn't tell you, your GPA is not going to capture that information or that aspect of your life, right? So there's always a little bit of loss of information in dimension reduction, and that's part of it, right? SAT and GRE scores, it's trying to take this complex idea of intelligence, and there's no great way to measure intelligence. And it reduces it down to 3 numbers, right? Or 2 numbers, your verbal score, your math score, and maybe a writing score, and things like that. And I guess schools are supposed to decide whether you are intelligent enough or not for admission based on those 2 or 3 numbers. So we're taking a complex thing, probably many facets, many dimensions to it, and we're reducing it down to 2 or 3 numbers. Other things, I don't know if you guys are familiar with the credit score and stuff. Maybe you have a credit card in your own name. You probably have some student loans in your own name. Student loans generally don't take credit score into account, I think by law, because they didn't want, it used to be student loans were tied to like your credit rating, but then only rich people could get student loans, and then that made only like education available for rich people, and then so the law said we're not allowed to do that, like that's not fair. we got to make education accessible for everyone. And the bank said, well, I don't want to give money to this poor person because I don't know if I'm going to get my money back, right? And so that's why student loans come with the student loan debts will never go away, right? Like if you declare bankruptcy, like you don't owe your credit card companies money anymore. You just say, sorry, I can't pay you back, and the credit card company has to go, okay, that was my bad. I shouldn't have trusted you with the money. But with a student loan, if you declare bankruptcy, you still owe the bank money because they said, the only reason why I gave you the money was because the law told me that I had to give you the money. Well, anyway, but so anyway, usually banks will just use two numbers to decide whether you get a loan or not. One's going to be this credit score, and the other is how much money you make. And based on those two numbers, they'll decide whether they'll give you $300,000 to buy a home or not, based on those two numbers. And so that one number, your credit score, takes into account a whole bunch of stuff about like how trustworthy you are regarding your finances. Like, have you been paying back everybody that you've owed money to? Do you already owe a ton of money? Have you ever declared bankruptcy, or have you ever gotten a negative remark on your things and things like that? And so that's just, it takes a bunch of things that are related to trustworthiness, financial trustworthiness, to a single number, okay? If you watch football, there's something called the passer rating, and this is what quarterbacks, they get some kind of measure of performance for a game, and this takes into account things like how many passes did they attempt, how many passes were made, how many passes were completed, and how many yards total were passed, and things like that. And it reduces, a performance over a game, or an entire season or career, down to a single number. And these things are all very useful because it allows you to kind of compare maybe two players who might have different play styles, okay? But you can kind of compare them based on a single number, right? So one person can be like, they only make short passes very frequently that are with high success rates, and that would factor into their passer rating. And then someone else maybe has a different style where they throw much longer passes, with a slightly lower completion percentage and things like that. How do you compare these two different players? Well, by reducing them down to a single number, you can compare them directly, things like that. Okay, or other things like in the Olympics, you have the decathlon and heptathlon and things like that, and they're basically competing on several events, and we're reducing them down to a single number so that you can rank them from gold, silver, bronze, and things like that. Okay. Okay, so that's kind of the idea of dimension reduction. And so now I'm going to venture into the math part of PCA, okay? So I've just wrote out all of that stuff, and all right, and so now, basically, for PCA, what we want to do is we want to project from m dimensions down to d dimensions. Okay, and so what PCA will do, so d being a number lower than m, right? So d is less than m. So we start off with m dimensions. This is kind of our high dimensional, and we want to project down to d dimensions, where d is a number less than m. And so PCA is going to define d different vectors. Which we'll call W sub d, and each vector is m-dimensional. Okay, so it's going to define d m-dimensional vectors, and each vector w sub d is a linear combination of the original m vectors. Okay, so imagine, kind of an analog is projecting a two-dimensional shadow from a three-dimensional object. Okay, so we can have some kind of object in 3 dimensions, and then when you cast light on it, it's going to produce a shadow on a surface, and that's a two-dimensional shadow, okay? And so what you have done is you've reduced the higher dimensional thing, the 3-dimensional, down to a 2-dimensional structure. And so if, let's say I call this x, y, and z, all right? You can imagine I've got some kind of, I don't know, some kind of cylindrical object, okay? And one possible projection is I could just cast straight down to kind of PC1 and PC2, okay? And so imagine, I guess just imagine like a toilet paper tube type of thing, and I could just cast this directly kind of this way, where each principal component is just a linear combination of the others, okay? And in this case, principal component 1, PC1 is just going to be all x, none of y, and none of z. Okay? And then PC2 is all of y, 1 for y, 0 for z. Okay? So it's just it's technically a linear combination of some of the variables. It's just that I've put 0 weight on x and 0 on z, and over here I put 1 on x and 0 on y and z, and things like that. Okay, so that's one possible projection. Okay, but somebody else could take the tube and project at an angle, and you would get maybe something that looks like this. So you get a bit of curvature on this end and a bit of curvature on this end, and maybe this captures a little bit more of what the shape of the tube looks like or something, okay? And I'm not exactly, I don't know what PC1 is. It's some combination of the components x, y, and z, same as PC2. Okay, so just some combination, linear combination of x, y, and z. Okay, we're just kind of moving the light around, and we're projecting down to a two-dimensional surface, and so we only get a shadow of a representation of what the object is. Okay. Is this notion of kind of projecting down okay? And we're just basically doing the same thing, except just in higher dimensions, and it might be like your original data set is 20 dimensional and you're projecting it down to 4 dimensions or something. So that we can't really visualize because we don't quite know how to visualize 4-dimensional data, but it's the idea of projecting a higher dimensional structure down to something something lower, okay? And so what we're going to say is that the dth element of the projection, okay, is going to be, so, you know, we project this down. This is the, yeah, okay. X and d is we're going to take our vector w sub d, and if we transpose this, and we'll say our original data is, you know, vector yn, this is going to be kind of the single element value, right? So w is, you know, some kind of weight, and it's sorry, this is, well, I'll just say WD transpose is going to be 1 by m, okay? And then yn is, okay, m by 1. This is kind of your original data. For observation n. Okay, and then when you do this projection, it's going to reduce this down to a single value. Okay, so we've taken the nth observation and we've turned it into one value. Okay, so the nth observation in m dimension, which is our vector y sub n, is reduced to a single value, x n d, okay? And this is, it's kind of the dth element of the projection there. Okay, and what we want is, we want to maximize the variation captured in the resulting projected space. Okay. And we've got a couple rules, okay? So one rule is that each projected dimension is orthogonal to all other projected dimensions. Okay, that is to say that if I've got some vector w sub I and I cross that, or take that against w sub j, this is going to equal 0 for all pairs of I and j, where I is not equal to j, okay? And then, and just to kind of help us, we'll just kind of set kind of a constraint that all vectors have a length of 1. So that is to say Wi transpose Wi is equal to 1. Okay, so that's what we'll kind of start with that. Okay, and also to make our life a little easier, we'll turn all of the original data, the y's, and we'll center it. Okay. Okay, so so this just basically means subtract the column mean from each column. So we'll do kind of the vector of means is going to be 1 over n times basically the vector y bar, so n for n equals 1 to n, and we'll set everything equal to 0, okay? So just subtract the column mean from each column, and then now we can start working with the PCA, okay? And so what we're going to do is we're going to kind of try to let's find kind of the first kind of principal component. And what we're doing is we're going to just take the vector y sub n vector for an observation, for observation n, okay, which is y sub n, which is a d-dimensional vector, I'm sorry, a m-dimensional vector. And this will get projected down to a single scalar value. Okay, which I will just call xn, okay? Because for the first principal component, we're going to just say let d equal 1, okay? So xn, and basically we're looking at w sub 1, and so xn is going to be basically equal to our w vector times our y vector, okay? And what we want is that we want the result so that to maximize the variance captured in this projection. Okay, so y is complex, and if we have to reduce something complex to a single number, we want that single number to kind of capture the most amount of variation, okay? So that when we take all of our data and we reduce each individual observation in our data down to a single number, we want the resulting numbers to be, as different as possible. So, so the variance of this data, okay, the variance of the projection, is sigma squared. And how do we calculate the variance of the projection? Well, it's, I'm going to just do 1 over n rather than n over n minus 1, okay? And it's going to just be the difference between each value xn minus the mean x bar, okay? So there's no, these are all scalar values here because we've projected it down to just one value, xn. xn is a scalar, so I can just kind of go off of this. All right, what is the value of x bar? Okay, so recall that we assumed or forced the mean of our y to be 0, okay? So if we talk about what is x bar is going to be equal to 1 over n times our w vector times y for all n's, right? And so we can actually pull this out. And we forced this to be equal to 0. So our x bar is going to be 0. Okay, so because x, all we're doing is we're just taking w's and multiplying. We're taking our vector w and multiplying it against our y, and we forced the y to have a mean of 0. Okay, and so therefore our x's will also have a mean of 0. Okay, and so okay, so this simplifies our variance. Okay, so our variance is simplified. Okay, we used to say sigma squared is 1 over n times the sum of xn minus x bar squared, but now this is 0. Okay, so we get 1 over n sum of x of n squared. Okay, which keep in mind xn is equal to w transpose yn as well. So this is also equal to 1 over n times w transpose yn. Right. Is that okay? I guess from n equals 1 to n. Yes, squared. Thank you. All right. So far, so good? All right. And okay, so continuing this on. Okay. So we've got sigma squared is equal to 1 over n of w transpose yn squared. Okay, and so I'll expand this out. So now we're dealing in vector notation again. Okay, so this has become and so in order for this to all kind of work out, it's going to be w transpose yn transpose w. Okay, so this is still a scalar value. Okay, so if we if I label these, where am I? Like w transpose is 1 by m. This is m by 1. This is 1 by m. This is m by 1. Okay, so this is a 1 by 1 if I do that, which makes sense because everything so far has been 1 by 1, okay? And so I'm going to pull out the W transpose, and I've got 1 over n, yn transpose W, okay? And does this look like anything? Well, here, let me do this, okay? So keep in mind that y bar is equal to 0. So I can also write it like this. I can do, I left out the sigma. Cheating. Okay. Yn minus basically the 0, which I can just write as y bar, times yn minus y bar transpose. Does this look familiar? Maybe? This is the covariance matrix, right? Okay, so what we have now is we've got sigma squared is equal to W transpose times, I'm going to write it like this, our covariance matrix W, okay? Where C is the covariance matrix of Y after being centered. Yes?
If we don't center in the beginning, all this would still work. We just get the actual values for the mean.
Let me think. So the definition of the y's, I'm just trying to think if we don't center it, what happens? I have to think about this for a second, for the relationship between the non-centered x bar and all of this. Okay, so far so good, getting up to this point. So now we've got our, this sigma squared, this is kind of the variance of the projected data, right? Okay, so the variance of our projected data is just W transpose, whatever, our W is kind of some kind of linear combination, weights for linear combination of our Y terms. And so the variance of the projected data is just W transpose times the covariance matrix. W transpose W around the covariance matrix of the original data. Okay, and so we've got this result. Okay, and we want to find our vector W that will maximize the quantity that will maximize this quantity, right? Subject to the constraint that W transpose W is equal to 1. So we're not going to just pick the biggest W possible because that's cheating, right? So subject to the constraint that W transpose W is equal to 1, okay, we want to find the W that's going to maximize this resulting quantity, right? because this is this represents the variance of the projected data. Okay, so if we are going to do this, we can use a Lagrange multiplier subject to constraint. So we're going to say L is equal to this times this minus lambda times the constraint. Okay, so we've got this constraint, we put that in here. Okay, and we do this, right? And then so to maximize, we take the derivative, set it equal to 0. So we're going to do, this is going to be 2 CW minus, this part becomes 2 lambda, and the 0 goes away. And we'll set this equal to 0. Okay, so LDW. So this is what we have. I'm sorry, and I left off the W here. Okay, so keep in mind lambda is a scalar, and C is a matrix. Okay, and so if we want to solve this, we're in a situation where we've got some matrix C times W is equal to some scalar lambda times W. Okay, so I've got a matrix times a vector is equal to a scalar times a vector. All right. Does that look familiar? What situation are we in now? So for this to work out, W has to be what? What's the relationship between W and C now? That for us to have a matrix multiplied by some vector is equal to basically just a constant times that vector. The relationship between W and C is that W has to be an eigenvector of the matrix C. All right? So in order for this relationship to work, the vector W must be an eigenvector of the matrix C. Okay, do we remember that? How eigenvectors work? Okay, so so when you multiply something by a matrix, it generally will like transform our data and stuff. But then, so if you take a matrix and you multiply it by a vector, usually it will cause the vector to point somewhere else. Okay, but in some cases, there's certain vectors called the eigenvectors of the matrix, such that even if you multiply the matrix times the vector, it ends up pointing in the exact same direction. It might have changed by some scalar value, but it ends up pointing in the same direction. And so that's what we need to do. Okay, I think we're going to run out of time. So on Monday, we'll wrap this up, and we'll look at some applications of this. But I'll see you then. Have a good weekend, and see you 10th week.